This is REALISATION-THERMAL-AI, a Cyprus Research and Innovation Foundation project on real-time thermal simulation of electrical substations using GPU-accelerated computing and artificial intelligence. Hosted by KYAMOS Limited in Cyprus, co-funded by the European Union through Next Generation EU and the REPower EU component of the Cyprus Recovery and Resilience Plan, the project ran over 12 months and delivered all 20 contracted outputs on schedule. Electrical substations are critical infrastructure. Busbars and conductors carry kiloampere-level currents that generate joule heat. If dissipation fails, insulation ages, ampacity margins shrink, and unplanned outages follow. Today, monitoring relies on sparse point sensors, thermocouples, fiber optic probes, infrared cameras, which cannot capture the full volumetric thermal state of a substation. The thermal behavior between sensor locations is effectively invisible to operators. Physics-based simulation can reconstruct the complete thermal field. Traditional methods, finite element and finite volume, are accurate but slow, and they require substantial engineering effort per scenario. For the parametric studies that modern substation design demands, evaluating tens or hundreds of configurations, this cost becomes prohibitive. Our approach pairs a fast GPU-accelerated simulation backbone with an artificial intelligence surrogate that delivers results in milliseconds. The solver core is a Lattice Boltzmann method with multiple relaxation time collision, based on the D3Q19 velocity set, with Boussinesq buoyancy coupling, per-region material properties, and a volumetric joule heating source term. Implementation is in CUDA-C++ with CUDA-aware MPI, permitting direct GPU-to-GPU halo exchange over InfiniBand, bypassing CPU staging entirely. The solver runs on the KYAMOS cluster of 21 Tesla V100 GPUs across 4 nodes, within CCL-based distributed data parallelism and bitwise identical results verified between single-rank and multi-rank execution. The solver was validated against 5 independent benchmarks. Poisson wheel channel flow for the wall boundary condition, NRMSE 3.4%. One-dimensional thermal source with MPI halo exchange, L2 error of 1.73 times 10 to the minus 4. Heated cavity at Rayleigh 0 for pure conduction, Nusselt error of 0.008%. Heated cavity at Rayleigh 10,000 for coupled buoyancy, compared against Daval-Davis, Nusselt error of 0.4%. And multi-rank versus single-rank consistency, bitwise identical. All 5 pass, coupled buoyancy cases below 0.5%, among the stricter quantitative criteria available in the open literature for this regime. The two-dimensional parametric campaign comprised 40 scenarios across 5 inlet velocities for volumetric heat source amplifications and 2 lateral boundary conditions. The sweep spans the Richardson-number range from buoyancy-dominated natural convection through mixed convection to flow-dominated forced convection, Reynolds numbers up to approximately 5,000, Rayleigh numbers from 10,000 to 10 million. Energy conservation residual across all 40 scenarios, 0.054%. The effect of inlet velocity on the thermal plume is shown here. At 0 inlet velocity, on the left, the plume rises vertically under buoyancy. With increasing wind speed through the center panel, the plume progressively deflects. On the right, under fully forced convection, the plume is almost entirely shear-dominated. The transition is smooth and physically correct, consistent with established natural-to-forced convection transition behavior. The project then progressed to 3-dimensional simulation at 3 scales of complexity. First, a full-scale real STL geometry at 845,000 cells. Second, a scaled surrogate campaign at 80 cubed resolution generating the AI training dataset. And third, the realistic multi-component air-insulated substation at 33.3 million cells, the production scale target. The full-scale real STL model was derived from a single-bay substation section with external dimensions 2.4 by 2.1 by 2.2 meters, voxelized at 3 cm resolution to produce 845,000 cells. The STL-mapped thermal field shown here confirms that the solver correctly resolves the individual busbars, conductors, clamp supports, and the transformer envelope as distinct heated features. Thermal plumes rise physically from heated components. The front view clearly shows the three-phase bus structure above the transformer tank. The three-dimensional scaled surrogate campaign covered 40 scenarios at 80 cubed resolution, 512,000 cells per scenario, producing the primary training dataset for the AI surrogate. The scaled representation uses an STL-informed analytical geometry that preserves the component layout at reduced resolution. Direct STL voxelization at that scale would result in subgrid busbars. Energy budget residual across all 40 scenarios, 0.006%. The realistic air-insulated substation is the headline simulation artifact. Geometry was generated automatically by the KYAMOS STL Substation Agent from engineering specifications, producing a three-phase substation section cropped to a single bay with one transformer, 3 bus phases, 1 breaker bay, 6 clamps, and routed jumper connections. The domain spans 8 by 14 by 8 meters and was voxelized at 3 centimeter resolution, producing a grid of 267 by 467 by 267, 33.3 million cells. The KYAMOS STL Substation Agent is a FastAPI microservice built on CAD query solid modeling. It exposes endpoints for health checking, preset listing, preset generation, and custom YAML-based generation. The component library includes busbars, breakers, clamps, transformers, routed jumper tubes, and support insulators, organized into 3 preset configurations that scale from a single junction prototype to a full yard-scale substation of 80 by 36 by 14.5 meters. Geometry generation completes in 1 to 5 seconds per specification. This cross-section shows the XY midplane at bus height, 6 meters from ground. The 3 parallel phase bus bars are clearly resolved as distinct heated features. The transformer thermal dome is visible in the lower portion of the image. The thermal pattern confirms that the 33 million cell grid correctly captures the individual conductor thermal signatures at production resolution. At transformer height, 2.1 meters, a 22 Kelvin hot zone is clearly resolved at the transformer tank surface. Thermal stratification extends upward, and the envelope heating is consistent with the volumetric joule source distributed through the transformer region. The XE midplane through phase B shows the busbar as a horizontal heated feature with a concentric thermal halo. The halo profile is smooth and symmetric, consistent with conduction through air from a cylindrical heated conductor. The YZ midplane at Bay 1 shows the full interaction. The transformer hot zone of 25 Kelvin at the lower left, and heat rising through jumper connections toward the 3-phase busbar region above. The intercomponent thermal coupling is directly observable. Mapping the thermal field onto the STL surfaces gives operators a direct engineering view. The surface temperature rise of each individual component. Maximum temperature rise, 24.7 Kelvin. Domain averaged rise, 2.82 Kelvin. Peak absolute temperature, 317.9 Kelvin. Energy budget residual at step 10,000, 0.59%. The full transient evolution of the thermal field over 10,000 solver steps shows the progression from uniform ambient to a steady-state thermal distribution. The hotspot locations emerge early and remain stable. The plume structure deepens monotonically. This simulation, running across the cluster of 21V100 GPUs, completes in approximately 60 minutes of wall clock time. 60 minutes of wall clock time per scenario is useful for design, but too slow for operational decision support. The answer is an AI surrogate, TUNet, a proprietary time-aware encoder-decoder architecture trained on the simulation data you've just seen that reproduces the thermal field at a fraction of the cost. Here are the headline numbers. The two-dimensional TUNet champion achieves a mean absolute error of 0.273 Kelvin, with 341,857 parameters, 23 times smaller than a standard UNet baseline. The three-dimensional scaled surrogate with 8-way test time augmentation drops the mean absolute error further to 0.0042 Kelvin, 6.5 times better than the two-dimensional baseline. On the realistic AIS at 33.3 million cells, the model holds at 0.0186 Kelvin global mean absolute error, or 0.022 Kelvin masked to hotspots above 1 Kelvin. Inference latency, 4.6 milliseconds on the compact model, representing an end-to-end speedup of approximately 21,900 times relative to direct simulation. Checkpoint size, 1.4 megabytes. Integration mean absolute error end-to-end, 0.018 Kelvin. The detailed comparison against a standard UNet baseline at the two-dimensional scale. The TUNet champion reduces mean absolute error by 53%, root mean square error by 51%, and maximum error by 46%. Parameter count falls from 7.76 million to 341,000, 23-fold reduction. Checkpoint size from 31 megabytes to 1.4 megabytes, 22-fold reduction. Inference latency is identical between the two models. The TUNet champion is strictly better or equal on every metric. Scaling to 3 dimensions with the scaled surrogate campaign improves accuracy further. Mean absolute error drops from 0.027-3 Kelvin in 2 dimensions to 0.042 Kelvin in 3 dimensions, a 6.5-fold improvement. Test time augmentation provides an additional 26% reduction over single-pass inference. Parameter count, 4.1 million. Training time, 1 hour and 10 minutes distributed across 21V100 GPUs. The 3-panel comparison. Top row is the ground truth solver output, middle row is the TUNet prediction, bottom row is the absolute error. 3 test scenarios spanning natural convection, forced convection, and an amplified source case. The AI prediction tracks the ground truth closely, plume structures, gradient regions, and hotspot locations, all reproduced. Absolute error is visually dominated by a thin shell at the domain boundary and is otherwise close to 0. Here is the critical result. The TUNet champion, trained on the scaled campaign and fine-tuned on realistic AI subvolumes, applied to a 128-cube test subvolume of the full 33 million cell substation geometry. The 4 panels show, from top left, the conductor band geometry, the solver ground truth, the AI prediction, and the absolute error field. For this scenario, mean absolute error is 0.033 Kelvin. Wall clock time, the solver takes 60 minutes, the AI, 164 milliseconds. Across the full test set, the realistic AIS model achieves 0.0186 Kelvin global mean absolute error and 0.022 Kelvin when masked to hotspots above 1 Kelvin, meaningful accuracy where it matters. Inference latency, between 163.8 and 168.7 milliseconds on a single V100. The training convergence curve, on a logarithmic scale. Validation mean absolute error starts at 0.6 of a Kelvin at initialization and decreases to 0.02 Kelvin by the end of 40 training epochs, a continuous improvement of more than 2 orders of magnitude, with no plateau and no instability. The project deliverables combine into a single end-to-end pipeline. An engineer specifies a substation layout as a YAML configuration. The STL Substation Agent generates the geometry. The GPU Lattice Boltzmann solver produces reference thermal fields. The TUNet surrogate is trained on those fields. At inference, the complete pipeline, from engineering specification to thermal field prediction, runs in seconds. The system architecture comprises 4 main components. The GPU-accelerated Lattice Boltzmann solver running on the KYAMOS V100 InfiniBand cluster. The STL Substation Agent, a FastAPI microservice. The TUNet surrogate deployed behind HTTPS APIs, and the dual client access layer. A WXWidgets desktop application for operators, and a WebGL browser viewer for design review workflows. Intercomponent contracts are JSON schema defined throughout. The end-to-end integration test. 5 WP5 success criteria, all pass. Integration accuracy, AI versus solver, target less than 1/10 of a Kelvin, achieved 0.018 Kelvin. Compact footprint latency, target less than 50 milliseconds, achieved 4.6 milliseconds. Realistic AIS subvolume latency, target less than 500 milliseconds, achieved 164 milliseconds. Latency stability over 100 consecutive calls, target sigma less than 5 milliseconds, achieved sigma below 0.5 milliseconds. And dual client path, target both desktop and browser operational, achieved, WX widgets and WebGL both validated. All 5 pass. Everything you've just seen ran on the KYAMOS V100 InfiniBand cluster, 21 Tesla V100 GPUs across 4 nodes, connected via Mellanox InfiniBand, with NCCL, distributed data parallelism, and CUDA-aware MPI. The cluster supports both the full-scale 33 million cell simulations and the multi-GPU AI training campaigns that underpin the results shown. To summarize, the solver was validated against 5 benchmarks, all pass, below 0.5% on coupled buoyancy cases. The 2-dimensional parametric campaign ran 40 scenarios with an energy budget of 0.054%. The 3-dimensional scaled campaign ran 40 scenarios at 0.006%. The full-scale Real STL ran 3 showcase cases at 845,000 cells. The realistic AIS ran 20 scenarios at 33 million cells with a 25 Kelvin peak temperature rise. The STL geometry agent provides parametric substation generation as a FastAPI service. The 2-dimensional TUNet champion reaches 0.0273 Kelvin, mean absolute error, 23 times smaller than the baseline. The 3-dimensional TUNet reaches 0.0042 Kelvin, 6.5 times better than 2 dimensions. Inference at 4.6 milliseconds represents approximately 21,900 times speedup on realistic AIS. The TUNet architecture is held as trade secret with a post-project patent decision gate. And technology readiness level 6 has been achieved, an integrated system validated in a relevant environment on realistic substation geometry, with the post-project roadmap targeting technology readiness level 7 through 9. REALISATION-THERMAL-AI is a project of KYAMOS Limited, funded by the European Union through Next Generation EU and the Republic of Cyprus Research and Innovation Foundation under the REPower EU Component 6.1. For more information, please contact the project coordinator at Apapadakis at KYAMOSMultiphysics.com. Thank you.